Hello everyone, my name is Aldo and in this video I'm going to talk about a joint project with Julian Fersan and Luis Franco. The title of this talk is the dynamical Schur number. Okay, let's begin with a review of combinatorics. A coloring is an assignment of colors to the elements of a non-empty set. For example, in this graph, we may assign the color green to the vertices A, C, and D, and the color orange to the vertices B and E. With this coloring, the resulted graph is this one. Or we may also consider the assignment of a different color to each vertex, like this one. But colorings are not exclusive to graphs. We can color many other mathematical structures. For example, the integers. We may consider the next coloring. We assign the color red to the even numbers and the color blue to the odd numbers. This coloring results like this. Or we can color the first four numbers with orange and the second ones with green, as you may see. Okay, a coloring is said to be monochromatic if all its elements have the same color. In this example, either the sets A, C, D and the set B and E are monochromatic. In this other example, the set of even numbers is monochromatic and so is the set of odd numbers. A K coloring is a coloring that uses exactly K colors. This is an example of a 2 coloring, and this is an example of a 5 coloring because we are using exactly 5 colors. And this is another example of a 2 coloring, and this is another last example of a 2 coloring. All these definitions fit naturally into Ramsey theory, which is the branch of mathematics that studies the existence of order within sufficiently large mathematical structures. In particular, we will focus on the integers and on a very well-known result called Schur's theorem. This theorem tells us that whenever we color the integers, we are forced to find monochromatic solutions to equations, okay? More precisely, the theorem states that for every integer k greater than or equal to 1, there exists a smallest positive integer s of k, such that for every k coloring of the integers 1, 2, and all the way up to this number s, there exists at least one monochromatic solution to the equation x plus y equals z, where x and y are not necessarily distinct. Okay? These numbers s of k are known as the Schur numbers. Now, in order to give an example of this theorem, we are going to look at the two-color version. The two-color version of the Schur's theorem states that every two coloring of the integers 1 up to 5 contains at least one monochromatic solution to the equation x plus y equals z. Let's prove this theorem, okay? Without loss of generality, assume that color red is assigned to number 1. It is easy to see that if number 2 is also colored with red, then we have a non-possible configuration. Then number 2 must have a different color. Let's say the color blue. Here. Then we assign the number 3 with color red. And then observe that the number 4 can be assigned with color red since 1, 3, and 4 is a non-possible configuration. And it also cannot be assigned with color blue because 2 and 4 have the same color and this is another non-possible configuration. Therefore, number 3 may not be assigned with color red, hence we assign it with color blue. Observe that number 4 must be assigned with color red, otherwise 2 and 4 have the same color, like as we previously see. And finally, observe that no matter which color we assigned, with number 5, it yields to some monochromatic solution. Analogously, if we would have assigned number 1 with color blue. Thus, the statement holds, and this finishes the proof. Now, the only known Schur numbers are for 1 up to 5 colors. And an historical note, the Schur number for 5 colors was actually discovered and proved in 2017. And this yields to an open problem pretty interesting. Okay, so in this work, we considered a dynamical approach to the problem of finding the Schur numbers. In order to enunciate the main definition of this work, we define the function t as the map of the interval 0, 1 to itself, defined by t of x equals x plus alpha modulo 1, where alpha is in 0, 1, and let's look at the dynamic or the behavior of this function. Okay, let's consider the interval 0, 1. And let's place an arbitrary point x sub 0. Okay, if we apply the function t to that point for an arbitrary alpha, the result is a jump of size alpha, like this. And now, if we apply the function t to this new point, the red point, yes, the red point, we obtain another jump of size alpha in here. And now, since we are taking everything modulo 1, if the jump of length alpha exceeds 1, then the map simply wraps around the circle. Okay, it spends part of the alpha jump, and whatever is left starts again from 0. Like this. Yeah. And the function follows the same dynamic in all of the points of the interval. Here we have x sub 3 plus alpha, x sub 4 plus alpha, x sub 5 plus alpha, and all the way up to many other points. Okay? Now, what we are going to do now is the following. We are going to divide the interval 0, 0, 1 in 2 equal parts, and we are going to color the points in the left part with red, and similarly the points in the right part with blue. Okay? Observe that this is a 2 coloring of the interval 0, 1. Okay, let's look at an example of this coloring with the function. Let's consider the same example as before. We were said that first we are going to part the interval in the middle, like this. Then we assign the color red with the points in the left part and the interval, and similarly with color blue the ones in the second part. Like this, and then the color points are in this way. Now, in order to save some notation, we consider the following expression. This is the expression of the nth iteration of t with itself, and is defined as t to the n of x equals x plus n times alpha. With this expression, we may find a more attractive and useful notation for the points of the interval. Here we have the points, and if we use the previous expression, then the points are like this. Now we are going to see another definition. Let's denote O sub n of x and t as the orbit of length n of x under t, which is the set of the points t of x, t to the 2 of x, and all the way up to 2 to the n of x. Okay, these points that you may see in this video. We say that an orbit is monochromatic if all its points have the same color. In the same example that we have seen, one monochromatic suborbit is this one, and another monochromatic suborbit is this other one. Yes, observe that all its points have the same color. Now, the main definition of this work is the following. For some k coloring of an interval 0, 1, with k greater than or equal to 1, the dynamical Schur number is the smallest integer n such that the orbit of length n of x under t contains a monochromatic suborbit with the form t to the a of x, t to the b of x, and t to the c of x, such that a plus b equals c. Okay, this is the smallest integer, the smallest length of the orbit, such that for a solution of the equation of the Schur's theorem to exist. Okay, and we denote these numbers by s of k comma t. In the same previous example, we have many examples of this definition, such as this suborbit, and observe that it satisfies the equation of the Schur's theorem, since 1, 4, and 5 is a valid configuration, right? And here we have another suborbit that satisfies the equation of the Schur's theorem. But even though these are possible solutions to the equation, since we are looking for the smallest integer, such that the definition of the dynamical Schur number is satisfied, then the dynamical Schur number of this example is 2. Okay, with this definition, we enunciate the first result, and it says that for any k coloring of interval 0, 1, with k greater than or equal to 1, we have that the dynamical Schur number is less than or equal to the Schur number of the combinatorics. Okay, and with this theorem, we enunciate the main theorem of this work, which is the following. For any initial condition x of 0 in 0, 1, and any alpha in the same interval, there exists a k coloring of the interval 0, 1, such that the dynamical Schur number is exactly the same as the one in combinatorics. Yes, exactly the same. And this is for every k greater than or equal to 1, okay? For every color. Now, with these theorems, we formulated the following question. How should the coloring be so that the equality holds? First, we noted that there exists some symmetry in the properties of the function t. We enunciate that for every k greater than or equal to 1, and for any alpha in 0, 1, we have that the dynamical Schur number under alpha is exactly the same as the one under alpha minus 1. Let's look at the idea of the proof of this theorem. We consider an arbitrary point, and we take its corresponding point at the distance of the middle point in the other interval. This point, okay? And now, if we jump an arbitrary alpha, is exactly the same as if we had jumped backwards on the other point, okay? And this backward jump is equivalent to forward jumps for the value 1 minus alpha, okay? It's like if I would have given all the rotation. And this happens with every point in the interval, like this and this, and tada. Okay? Now we are going to consider the regular k coloring, which is defined as it follows. For some fixed integer k greater than or equal to 1, we are going to divide the interval 0, 1 into the interval 0, 1 into k subintervals of the same width, 1 over k. And each subinterval is assigned with a different color. Okay? And now we are going to consider the colors as natural numbers. Without loss of generality, the first subinterval gets color 1, and the second subinterval gets color 2, and so on up to the kth subinterval, which gets the color k. With this definition, we are going to show the results for two colors, okay? The theorem of two colors holds that for the regular two coloring of 0, 1, and for every alpha in the same interval, the dynamical Schur number satisfies the following expression. It is 2 if alpha is 0. It's 4 if alpha is less than or equal to 1/6, 1/2, or greater than or equal to 5/6. And it is 5 if alpha is greater than 1/6 and less than 5/6, except 1/2, of course. And the theorem also says that the dynamical Schur number never lies in the value 3. We are going to prove this theorem. For the value of 2 is immediate since alpha is 0, then t and t to the 2 both lie in the same point as the initial condition. Hence, the dynamical Schur number is 2. Now, in order to prove that the dynamical Schur number never lies in the value of 3, we need to observe that the only possible configuration is 1. Is 1, 2, and 3, I'm sorry. Let's take an arbitrary point, x sub 0, and we apply t for some arbitrary alpha, okay? Observe that if if both t and t to the 2 both lie in the same subinterval, then the dynamical short number is 2, no matter where t to the 3 lies. If it lies in the same subinterval or in the other one, it's the same. This is because we are looking for the smallest length of any suborbit that satisfies the equation of Schur's theorem, okay? On the other hand, if t to the 2 lies in a different subinterval as the point t, then there is no possible way that the configuration has the same color. And these arguments conclude this part of the proof. Now, for the value of 4, we first assume that alpha is equal to 1/2. We take an arbitrary point and apply t. Now, observe that every integer is congruent to 0 modulo 1. Then it follows that 2 times alpha lies on the same point as x sub 0, this. And with a similar argument, 3 times alpha lies in the same point as t, this. And it happens the same to t to the 4. It lies in the same point of the initial condition, and that's the point of t to the 2. And it is easy to see that 2 and 4 are a monochromatic solution to the equation on the Schur's theorem, right? And this concludes this part of the proof. And now let's assume that alpha is less than or equal to 1/6. Then if we apply t, we jump this, and without loss of generality, let's assume that t to the 2 lies in a different subinterval as t, so that the dynamical short number is not number 2. Then for t to the 3 and t to the 4, these three values lies in the same subinterval. This is because because 3 times alpha is less than or equal to 1/2. In other words, t to the 4 cannot escape from the same subinterval as t to the 2. And it follows that the dynamical short number is 4. The case of alpha greater than or equal to 5/6 is analogous to the previous case, and this follows from the symmetry theorem. Easy, right? And finally, for the value of 5, let's assume that alpha is greater than 1/6, and let's take an arbitrary point, and we apply t. Without loss of generality, t to the 2 lies in a different subinterval than the one of t. We may observe that t to the 3 lie in the same subinterval as t to the 2, but t to the 4 escapes from this subinterval. This is because 3 times alpha is greater than 1/2, and it follows that the dynamical short number is 5. And this concludes the proof of the theorem. Moreover, since the dynamical short number is less than or equal to the short number in combinatorics, and we just proved that the short number of 2 colors is 5, then the dynamical short number is less than or equal to 5, and these are all of the possible cases for 2 colors. Now, we wondered, what if we slightly increase the number of colors? Unfortunately, we found out that for this kind of partitions, the dynamical short number does not increase that much. We enunciate the following theorem. For every k greater than or equal to 1, the dynamical short number is bounded above, and moreover is less than or equal to 4 times k minus 3. Okay, so in general, any regular k coloring of 0, 1 does not converge to the short number. And as a consequence of this theorem, we show that any coloring that attains equality between the dynamical short number and the classical short number has to be an irregular coloring. In order to approach this problem, we implemented a computational heuristic algorithm, although discussing it in detail would require a separate talk. In this brief video, I merely wanted to present our initial results. So, as conclusions and future work, we have the following points. To think about the problem of strict short numbers, which are related to the same problem as Schur's theorem, but in that setting, the 3 numbers are required to be strictly different from each other, okay? To think about the rainbow version of the Schur's numbers, and these are the Schur numbers in which the 3 integers must have different color. And we wondered if we could implement these dynamical ideas for some other problem in Ramsey theory, for example, the Ramsey numbers or Van der Waals numbers. And this is all. Thank you so much for watching this video, and bye bye.